And everybody has, very interesting and strong background, so feel free to contribute. I know very little. We all know some. Together we can know much more. Okay. So probably you will see angles that I don't see. Feel free to always, talk to me and everyone. Right? Ask me questions. Okay. So this course will be fairly mathematical. So linear algebra starts with something called vector space. What the heck is a vector space? It's like a whole bunch of objects you could add to each other, and you should be able to multiply those objects with a number. And whatever that adding means, you get to define. If those objects are, say, images, adding means something else. If those objects are literally numbers, adding means something else, right? If those objects are, I don't know, vectors in R5, adding means something else. So there will be an adding operation, and then then you should be able to multiply every object with a number, okay? So quick example, say R2. Here's my vector A, here's my vector B. And if I multiply A by a number 3, this is what happens. And then the addition is usually defined this way in R2. You just literally add coordinate by coordinate, okay? And now another vector space. These are shapes in R2, not necessarily just dots. Shapes that include the origin, 0, 0 in the middle of it. Doesn't have to be in the middle, just should be inside. So how do you add shapes to each other? You literally do the same addition on top, but you're allowed to add every vector inside this shape to every vector inside this shape, okay? So there's a book called Math with Bad Drawings. It's a bestseller. So, you should forgive my bad drawings at this point. If you can make a bestseller, So how do I add everything here to everything here? You imagine putting this guy on top. This is like a circle with radius 1. This is like a square. And like I put the square right here. And if you imagine putting the circle and moving it around, this is kind of the shape you will get. And multiplying with a number literally means like photocopically enlarging or squeezing. That's a vector space, for example, okay? I'm just trying to, put into your mind that when somebody says vector space, don't necessarily assume it's just like vectors with 1, 2, 3 in the coordinates. It could be a collection of whatever you're trying to process. You just need to be able to have two operations on them, multiply with a number, and add them to each other, okay? All right. The shapes, we may or may not use it, but we will use, say, images or whatever else. That's a vector space. And then if you remember back in the day, whenever you took linear algebra, when you have a vector space, you try to talk about something called bases, right? What's a basis? Like you should be able to take any object in your vector space, decompose it into basis elements. And there are many ways to create for the exact same vector space. And depending on your basis, the computational aspect could change a lot. For example, if you use this thing called JPEG file type, right, JPEG, the genius idea behind it was essentially to create a very smart basis for a collection of functions as a vector space, okay? That's called wavelets. And the person who invented it, I think this year, got a presidential award, Ingrid Daubetis from North Carolina. Well, I think she's originally from Belgium. Anyways, so the thing behind JPEG was just, you got a vector space, say images, and would like to decompose every element in that vector space into your basis elements. But depending on the basis you picked, how you do it on a computer could change dramatically. And that was a very clever basis back in the day. And electrical engineers probably knows way more than me on this, so I'm not going to talk too much about wavelets. But I think we will have one industry speaker who does some biomedical applications. He will touch base on this kind of stuff. And basis, let me just write what I said. If you got your vector space, say V, and if you got and let's make it concrete. Let's say my vector space is R2. And if you take our standard basis, E1 and E2, and if you take your X and try to decompose it, you kind of know what to do about it. This will be X1 times E1, X2 times E2. However, This doesn't have to be just this particular basis elements, as I said. You can change the basis as you like. Okay. And the word I said was called wavelets and JPEG if you're interested. Now let me move on. So now when you have these vectors and vector spaces, people would like to talk about norms. So what's a norm? Well, norm is a function that you give it an input, it spits out a number. That's what it is. Okay, you got your vector space. This norm comes over and says, this vector looks like a 5 to me. This vector looks like a 10 to me. It's supposed to be a measure of how big is your vector, vaguely speaking. Okay, that's what a norm is. So here are some norms you have probably seen before. Say I am in Rn. I have a vector where every coordinate is a real number. This is our standard Euclidean norm. We square the coordinates, x1 squared, x2 squared, x1 squared. Then we take square root of everything, right? Do you guys remember this from your analytical geometry, maybe in high school or whenever else? Depending on your background, it could have been a while you have seen this, or maybe you have just seen it today. It depends. Yes, go ahead. Magnitude is usually reserved more for numbers, not necessarily vectors. So let's say I got -5, the magnitude will be 5, right? For vectors, you usually call norm, but probably it's the same thing in the context you have seen. Yeah. The point I'm going to try to make will be there are different ways you could create a norm, and they will have different impacts on your algorithms. Okay. I'll give you some visualizations in a sec. Bear with me. All right. So if this looks too matty, just give me a couple of minutes. I brought some pictures. All right. So this is a norm called Euclidean norm. You square all the coordinates and you put a square root on top. This is another norm. This guy doesn't square anything. It takes every coordinate, takes absolute value, and then adds that up. Okay. For now, this may look technical. We will attach more meaning soon. Bear with me. And then you can pick any number p. It's actually between 1 and infinity. And there is something called a p norm. Okay. And it takes the absolute values, raises it to the power of p, then puts a 1 over p on top. For example, if you put p equals 1, you get this guy. If you put p equals 2, you get this guy. If you could put p equals 10, you'll get something else, okay? Another norm that is very commonly used is called infinity norm. You literally go pick the maximal coordinate, okay? So let me tell you a story that may help you remember this stuff. So I think this was maybe 3 years ago. Pandemic made the time very blurred for me, so I don't remember very vividly the timing, but I remember the story very vividly. So this person who called me was working for a hospital who does research on child cancer. And they were trying to cluster genetics data to understand what might be causing the child cancer. And then first I got, of course, a little mad. I'm like, do you literally do just basic clustering for child cancer, And they told me if I would have seen what doctors have been doing for centuries, I would like them so much. Okay, after we get past that period, we started talking, they asked for some help, and they do this clustering. What they get makes no sense to them, and makes no sense to doctors either. As I talked to them more, I realized they were using standard libraries, and they are all defaulted to this norm. You have some genetics data, like a vector here, suppose the coordinates are A, B, C, whatever DNA sequencing they're doing, and yet another vector here, and they want to measure how close are they to each other, all right? And then they use default libraries, which defaults to this norm. But in their case, this infinity makes much more sense because this is much more sensitive than this guy. If you change a little bit in that genetics data, the meaning changes just drastically because it's genetics. It's not just some numbers out there, right? And then I told them, probably you should use this norm. And they said, we have no idea how to use that norm. Then I told them another two, which I'm going to tell you in a couple of minutes, which allows you to use this P norms to approximate this one. And then in their case, I thought L8 or L10 would be a good proxy for this one. So they coded stuff up on themselves instead of defaulting in a library with L8. Like 3 weeks later, they called me and they said, it's like flowers beautiful. We figured it out. Yes, go ahead. Very good. So getting first question, and the second one, the other thing I said in the story, why I could approximate the infinity using some LP norms in the tree. Yes, very good. So now let's compute some examples. Let's say this is my vector, and I'm going to compute 3 norms, okay? Just to make sense on some sense of this stuff. So 1 over root 10, 1 over root 10, 1 over root 10. Okay, let's compute the 2 norm. Square the first one, 1 over n, square the second one. Square all of them. Since I have n of them, n times 1 over n, this is 1, okay? Now, L1 norm, it says I'm going to add up the absolute values. Right? So let me go back to definition. You see the definition of L1 norm right there, right? I'm adding every coordinate. And I have every coordinate 1 over root n, and I have n of them. So I got 1 over root n, the square root of n. And max, well, since they're all the same, max is easy, it's just this guy. Okay. Now, suppose you took this vector, right? And start messing with it a little bit. How much all this stuff will change? Or before maybe we go for it, we got the exact same vector, we did some computations, and the outputs are drastically different. This is a number 1. This is square root of n. If n gets bigger, this is going to be huge. Okay. And this is like such a small thing. All right. So what does this mean? This means intuitively, this guy, 1 norm, cares about more or less how many non-zero entries you got in your vector. Okay. This 1 norm likes sparsity. It would like to have a whole bunch of zeros here and there, right? That's what it is caring. This one is like a rounded ball that we are used to. This you'll get used to more, is a lot more sensitive. So let me show you some pictures of these. And now, okay, maybe with the sparsity remark, let me connect it to stuff maybe you heard or have seen. Did you guys heard of something called regularization or overfitting? Anybody like? So what does overfitting mean? You're trying to fit some model to whatever problem you're studying, right? You train stuff through data, and your machine learning stuff is fitting something on it, right? But after some point, it's like more or less stabilized. Nothing is changing in your model. So you say, now I'm good. Let me use this model for data that my algorithm have not seen before. And you use it, all of a sudden, it sucks so badly, you don't know what to do, all right? That's called overfitting. Why? Because your model gets so much complicated, okay? Now, intuitively say, this X was your model. Now, to regularize, you will tell to your model, right? Don't go above blah, blah norm. Don't make it too big in such and such norm, intuitively speaking, okay? And if you tell your model, don't go above, say, 1 in terms of this norm, this is just fine. But if you say don't go above 1 in terms of this norm, this is way above the charts, okay? So if you're going to regularize with L1 norm, your models will be a lot more sparse. They'll be much more simple, okay? But if you go regularize with L2, they'll be rounded, complicated, right? So it depends on what you want your model to do or not to do. You will pick your norm accordingly, and it will change the entire algorithmic scheme behind. I'll get into more precise details of this. But if you say call any library, say, I don't know, does anyone play with scikit-learn, the most one of the most basic machine learning libraries out there, right? So you call scikit-learn and you run some algorithms there. And all of a sudden it doesn't work. Why? Because the scikit-learn has an option to pick which norm in the backend. And if you never looked at it, it will default onto this one. In which case, maybe you should have done this one, okay? We'll get into all these. All I'm trying to say is trying to spend some time on what these norms may mean will pay off. They are not just some technical math, okay? Now some pictures. Yeah, go ahead. It literally counts how many non-zero entries are there. That's the zero norm. That's actually what you want to do. One is the closest proxy to zero. Usually you actually want to do zero, but it's just too much to ask for. It's not smooth. It gives you a whole bunch of trouble. You usually use L1 as a good proxy to zero. So that was a great question. Zero is literally count how many entries in your vector are not zero. That's what zero norm is. All right, now some pictures. This is some code by this person, Caden Mimak, on GitHub. So the work is on writing some code that will visualize unit balls for this P norms. What's a unit ball? Look at all vectors X that has norm at most one, okay? So for example, what is L2 ball? It's the unit ball we are used to, P equals 2, right? So now this code is visualizing for different P values, how does the ball look like? All right, so at infinity, you get a square. And there is also a 3D version of the same code. I thought it was a lot of fun to just stare at this when I was so tired. By the way, I should have said one thing. If my energy is a bit lower today, it's because I wasn't feeling so well, but it's not some infectious disease, don't worry. It's some stuff I'm dealing with. I did not want to cancel the course, so this may be the lowest energy you will see from me this semester. Okay. All right. Okay. So now, at least I hope intuitively these LP norms are making more sense. And let me draw you at least the L1 ball. This is the 2D L1. And the 3D of it will show up here soon. You see, the 3D octahedron shows up. Okay. Okay. Very good. So imagine L1 ball. And what kind of a vector, say, will have norm bigger than 1? And imagine the same thing with, say, L2. L1 is a lot more skinny. Okay. So it will not allow so much change in your vector if you use L1. L2 is much more rounder. L infinity is the biggest. Keep those intuitive pictures in mind, that's all. Okay? Yeah, right. I'm listening. In the genetics context, it was L infinity. I could explain more. It depends on context. Okay, here is the inequality I was talking about. You can compare this stuff to each other. Let me just, I wrote the general version here, but we will care mostly about L1 and L2. For 1 and 2, it will look like this. 1 norm will always be bigger than 2 norm. And it will be bigger than equal to 1 over root n times the 1 norm. Okay. That's mostly what you're going to use. And depending on which norm you use, the exact same algorithm will have different names. We will see them later. For example, if you're doing linear regression, and if you use this one, you'll get an algorithm called lasso in your scikit-learn library. If you use this one, you'll likely get something called hinge. etc. So you do the same exact algorithm, you just change the norms in the definitions of the algorithm, it will get a different name because it behaves very differently. Okay, yes. Yeah. Okay. So far, just norms and like some intuitive pictures about them, and the fact that you can compare them. Okay, this is called Hölder's inequality. You will mostly need only this one, but somebody can give you any two p norms you could compare. Okay. And if you need to remember, you could always go back to recording of this lecture and look it up. Okay. So I'll not test you on that. Okay, that's Hölder. And today I'll put you an exercise which will make you play with this a little bit. You'll just plug in some numbers to this Hölder thing and then get some output. This will be on Canvas after we're done. Okay, this is norms. And don't read this inner product stuff on the screen yet. So norms only tell you how big a vector looks like. And that bigness will be a proxy of some complexity of the vector, okay? But they do not tell you how two vectors are related to each other. They may only tell you how far away one vector to another, but they will tell you nothing about if there's an angle in between, how similar they look, not so much, okay? So for this, you would usually need an inner product. What's an inner product? Do you guys remember this thing called dot product? You take two vectors, you multiply coordinate by coordinate and add. Okay, that's an inner product, right? That's not the only inner product. You could have a whole bunch of different ones, but, and we'll get into this too, but an inner product is somebody who has these properties. We are working with real numbers. Some people work with complex numbers, especially electrical engineers may be working. We'll do only reals in this course, okay? So inner product will take two vectors and spit out a number, okay? That's what an inner product does. If you change the order of the vectors, x and y are two vectors, the output should not change. This thing with brackets, that's the inner product. And if you take numbers, a and b, multiply your vectors and do the inner product, it should decompose like this. And if you take inner product of a vector with itself, it should be a number that is positive, okay? That's what an inner product is. And every inner product also produces a norm as a side effect. So you take the inner product of the vector with itself, it's a positive number, you take the square root, that's the norm corresponding to this particular inner product you defined. But usually we would need inner products for this last thing. I'll get to this, don't worry about it for a sec. Let's look at here. You take the inner product of two vectors and you divide it by how big they were in terms of the norm given by that inner product. This will give you a number between 0 and 1 always. I'll tell you why, which is right here actually, okay? And that number will be cosine of an angle, and that's the angle in between, okay? So now you're able to relate vectors to each other because you have an inner product, okay? Take the inner product, do what I just said, and then you could find that angle, that's the angle. For example, people will take this whole bunch of words, then they'll make it a huge vector called word embedding, right? And then this LLM people will use something called cosine similarity. This is what it is. You make them a vector, take their inner product, divide with the correct normalization. This will be a number between 0 and 1. Look at which angle theta will give you that number as cosinus. That's it, okay? That's how they measure similarity between a whole bunch of words in sentences. But that's not the only way. People keep discussing what kind of similarity measure we should use. And one way to think about it is like, can I change the definition of the inner product so that this angle will change at the end, how it looks? And this is possible. We'll talk about it today or next lecture. Okay, and finally, let me explain you this. As soon as you have an inner product of two vectors, the number it spits out will be always less than equal to take the norms individually and multiply, okay? The only case they could be equal would be when they are literally the same vectors, or maybe a scaled version of the same vectors. Okay, yes. So this norm that is introduced by a vector will be always looking like an L2 norm. Okay, that's not literally the L2 norm I defined for you, but in essence it is. Take it that way. Okay. If you use different norms. So Farhan's question was, I take an inner product, it seemingly gives me a norm. What kind of norm is that? In the type of stuff we were talking about before. And my answer is think about it as P equals 2. Okay. And I'll be more precise on this later. When we talk about singular values and PCA, it will connect back to inner products and you will start seeing it more. Okay. It will be like a round ball always when you get an inner product and the norm of it. But the round ball sometimes looks like a soccer ball, like Europeans, or like an American football, depending on your inner product. Okay. That's the main thing. The axis of the ball could change. Maybe you squeezed it, maybe you stretched it, but it's going to be a L2 ball-like object. So over here. It's good, yeah. Yeah, sure. Angles are all defined by the inner product you introduce on your vector space. So So think about it this way. So orthogonal means not related at all. In terms of our purpose, that's what it means. Because if their inner product is 0, cosine, what kind of thing gives you cosine theta 0? Orthogonal. Okay. So what does it mean when we analyze data to be orthogonal? That means not related at all. Okay. And depending on your definition, this will change. What is not related at all? All right. So for example, think about your vector as like data. Every coordinate is a feature. Okay. Some inner product cares about the first feature so much. The other one doesn't care about the first one. It cares about the 10th one. Right. So depending on how you look at it, the angles will start changing. Right. And how you look at it could be determined by your particular application if you want. Yeah. All right. Very good. Now I will talk about matrices, but before matrices, I have to tell. So far, by the way, any questions? We didn't do too much yet, but it's a lot of concepts. So you might be feeling like we did a lot. Yeah, go for it. Yeah. It's recorded now. Yeah. It's recorded. I'll also give pointers on the textbook. And also we will have a Jupyter notebook usually after a class, I'll try my best to give you all that stuff. So you look around and also always feel free to ask me for more. Yeah, go. That I have to think because it's extra work. I'll think about it. Okay. So because I'm using a particular app, I have to extract, blah, blah, blah. All right. Anyways, so far so good. Very good. Now, what we did so far is like, what's a vector space? What are vectors? The type of norms we put on them changes. How big are they? And then an inner product. We defined the notion of an inner product in kind of an abstract way. Then I told you this gives you an angle. The reason I abstracted away is like there are many ways you could define an inner product on the exact same space. And it actually is very useful for a lot of algorithmic purposes. Okay. So I don't want to be abstract just to be abstract. Hopefully I'll always have a reason. Okay. All right. So next thing I need to tell you is like if you open any machine learning library, you will see something called a tensor. All right. It's either going to be called TensorFlow or PyTorch or blah, blah, blah. And then you'll have to use something called TensorDict in PyTorch, or TensorFlow is already called Tensor, whatever. So there will be this word tensor. Okay. What does that tensor mean? So for purposes of data analysis, a tensor is this Rubik's cube, right? So what is tensor? It's literally a data array which has a certain dimension. If it has n variables and order d, it will be n times n times n times n d times. All right. So this is a 3 tensor. And a matrix is a 2 tensor. And a vector is just a 1 tensor. Okay. So vector is just a vector. Now think about 2 vectors together, it looks like a matrix, right?
If you have 3, it looks like a 3D tensor. Okay, Rubik's Cube, kind of a distraction. It doesn't move around so much. Okay, that's it. Okay. And usually you use 3 tensors in most applications, maybe, but you can use as much as you want. You can go 4, 5, right? And just like decomposing matrices, you can decompose tensors also. But and tensors have a lot of other meanings in many different parts of sciences. If you're a physicist, for example, if I come and tell you a tensor is just a data array, you might not so be happy. Because for physicists, this means tensors record certain physical laws. That's why they use them. They will have a word called metric tensor, inertia tensor, blah, blah, blah. But for us, it's just a way to organize your data. And they are also used a lot in quantum computing. Who was quantum computing? Were you the quantum computing person? Somebody said, yeah, okay. Right, in quantum computing, they will have something called tensor networks to record whatever is going on in quantum computation. Tensors are all over the place. They're not easy to deal with. If anybody pretends they understand tensors so much, don't worry about it. I would say they're very complicated. The person I worked with in Berlin was one of the world experts on tensors. He used to tell me, God created matrices, they will turn them into tensors. They're quite complicated objects, but we have to use them anyway. All right, this is a tensor. I hope it makes sense. This is what it is for us. Either it's 3D, 2D, 4D place to record your data. That's it. All right. Now, the next thing we will do is we will start changing vectors from what they are to something else. We will act on them with something. We will do some process on them, okay? The most simple thing you could do on vectors is something called a linear map. What's a linear map? You take this X and Y, they were sitting peacefully, and somebody added them, okay? Then you did F on them. You changed them to something else, all right? But it should decompose, if F is linear, as number A times whatever has happened to X vector plus number B times whatever has happened to Y vector. Not every change will decompose such nicely, okay? And examples, if you're taking your vector X in R2, say coordinates X1, X2, if you're spitting out 3x1, 2x2, that's a linear thing. If you see squares like this, that's a nonlinear thing. And counterintuitively, this guy is also not linear. This 5 at the end does not depend on the vector at all. It messes up the definition. But this is a fixable nonlinearity, okay? That's not a big deal. You can get rid of 5 somehow and then put it back later. That's fine, all right? Now, why do I care about linear stuff? Everything linear, like this, can be recorded using a matrix, okay? For example, let's say your function is taking x1, x2, and sending it to 3x1 plus x2 and x2 in the second coordinate. Now, take this matrix that I put right there, 3, 1, 0, 1, and multiply it with x1 and x2. Do you remember vector to matrix multiplication? How do you do matrix vector multiplication? We have a lot of different backgrounds. Tell me if you don't remember. It's fine. I'll go over it again. Not a problem. So how do you do matrix vector? Take the first row, multiply it with the vector. 3 times x1 plus 1 times x2 gives you this. 0 times x1, 0 plus 1 times x2 gives you this, okay? So this function is represented by this matrix if I am using the standard basis. The function will remain the exact same thing. Here is your function. But if you change the basis you use, the matrix representation will change, okay? This is a good point to keep in mind. Functions are functions, you define them, they don't change. Good. But if you change the basis, if you change the way you look at your vector space, the matrix representing it will change, okay? For example, suppose you go from E1, E2 standard basis to something else. This function will not change at all, but this guy will look very different. Okay, just keep that in mind. Yeah, go ahead. Exactly. So screen space to what space you said?
Exactly. So I'm more familiar with world screen because I work with some computer vision people, but I would guess the same. So let's say your camera is a matrix that takes 3D vectors, makes them into 2D vectors. And this could be recorded like a matrix right here. Or in computer graphics, you take stuff and you turn it around, right? These operations are all represented by matrices, okay? And the stuff that turns around is specific, right? So it's not stretching it, it's not squeezing it, it's just turning it around, right? So that must be a specific type of matrix, not just some random matrix out there. And yes, we will see that matrix soon. It's called orthogonal matrix. That represents the rigid motions around. So very good question. So all the standard routines you might be using in your environment, not all, but good chunk of them will be represented by some matrices, and that's how computers will make them going through number chunks. Computers have no idea about geometry, right? Very good question. And then if you keep stacking linear stuff on top of linear stuff, what do you get? A deep neural net. Okay, that's what it is. Or at least that's the beginning. It was linear stuff on top of linear stuff. Then they put nonlinear, blah blah blah. Right. So that's called multi-layer perceptron. Okay. All right. Okay. So this is now matrices are not only like a place to store data now, they also represent some action. Okay. Don't forget this. And I need a small regression. I'm so tired today. Not regression, digression. All right. Which is, I need to remind you what's a transpose of a matrix. So do you guys remember this transpose stuff or not? I see mixed response. Some people are like, yeah, of course. Some people are like, it's good to remind me. So I'll do that. So let's say you got your matrix here. Let's say this was your B. So do the transpose. You should make the rows columns, basically. You take it, you turn it around, okay? So 5, 2 now will become the first column, and 3, 1 will become the second column. That's what a transpose is, okay? Take this, turn it around, right? Okay, now why do I remind you transposes? Because they are very much related to inner products and some other stuff we will discuss. If you have a matrix, if you have a vector X, you act on it with your matrix A, then you happen to compare similarity with some vector Y. This will be the same if you would do the transpose matrix operation on Y and compare it with X. These are literally equal things, algebraically, okay? So inner products and transposes play out very well. So far, okay. Now, we are thinking about matrices, like doing some stuff. We do it through like matrix to vector multiplication. But we see it like kind of a very local way now. I take a vector, I multiply with a matrix, I got something out of it. And I don't really fully understand what the matrix is really doing, okay? Okay, it's doing something on my vectors, but I'm not really sure what is it doing. And this is not a new problem. As soon as people started thinking about matrices, they ask this question. How do I look at a matrix and kind of see what this is gonna do to my vectors? Then after some point, they said, I don't wanna see it, I wanna hear it. Okay, I'll tell you maybe what that means, all right? Then they started developing like techniques to read off from matrices what they're gonna do when you use them as an operation, because it's not clear at all. Suppose somebody gives me a 1,000,000 to 1,000,000 matrix, whole bunch of numbers. I have no idea what this is gonna do, right? Okay, so somehow you need to simplify and extract the essence of that matrix and see what it is gonna do to your vectors when you let it act on them. And turns out some of the people who thought about this was Germans, and in German you would use the word eigen for something intrinsic. For example, if somebody is intrinsically motivated, you would say Eigeninitiativ. So this person is like taking self-initiative, right? So then the notion get into English. I don't know why it happened. It's called eigenvalues and eigenvectors, okay? This is a German word. And in German, you can take as many words as you want and combine it into one word. That's kind of what happened. Eigen and value became eigenvalue and eigenvector. Okay, so here is the definition they come up with. If my matrix is taking a vector, and all it is doing to my vector is like take the same vector and multiply it with a number, then this vector seems to be catching something essential about this matrix. Okay, they call that vector eigenvector. It's like an intrinsic vector in terms of this A transformation, and the value lambda as the eigenvalue. And if you look at all the eigenvalues of your matrix, somehow that tells you what this matrix is going to do. Okay, we'll get to how it tells you what it is going to do. This is literally called spectrum of your matrix. You know, this chemistry people would do spectrography, right? So they'll have all the spectrum of elements and stuff. And this is the exact same idea. You look at your matrix, you look at the spectrum, somehow you will see what it does. Okay. Now, how many of those I will have? If you have an n by n matrix, it will have n complex eigenvalues, but we don't like complex stuff in this class. We want real numbers. Yeah, go ahead. Yeah, some eigenvalues will be 0. Let's say AX happens to be just 0, 0, 0, 0. Say your matrix A is taking your vector X and just literally killing it entirely. Okay? It's the same as this lambda is 0, right? 0 times any vector is 0. This lambda is a number, X is a vector with a whole bunch of coordinates. Yeah. Yeah, we'll get to that. Give me a sec. I got some pictures and visualization. Yeah. But very good question. Keep the question in mind. Yeah, okay. So now, every matrix will give you n complex eigenvalues defined this way. That's a mathy fact. But it's hard to kind of understand, at least for me, complex numbers. So I'll try to see what kind of matrices will give me real eigenvalues instead of necessarily complex numbers. And that's mostly what we will use, okay? And also, some eigenvalues might be appearing more than once. For example, if you look at this matrix, 1, 1, 1, 1, 1, and if you look at the eigenvalues, you will have 2 of them. That's what the math fact is. It's 2 by 2 matrix. You will end up seeing 2 eigenvalues. And turns out for this guy, they're both 1. You see 1 and 1 again. Sometimes it could repeat itself. But in total, there will be n of them. Okay. For symmetric matrices, all the eigenvalues will be real. What's a symmetric matrix? If you take transpose, and if that doesn't change anything at all, that's a symmetric matrix. Okay. When you look at a symmetric matrix, it looks like this. You see the matrix. Here are the diagonal entries, right? And whatever you have off diagonal, the same thing will appear here. It's going to be literally looking symmetric. If you see off the diagonal, say, second entry, say 2, and you will see again a 2 here, okay? That's why when you do transpose, nothing changes. That's what a symmetric matrix is. And in that case, all the eigenvalues will be literally real numbers. Then we could work with them much easier than some complicated complex numbers, okay? So we'll mostly deal with symmetric matrices. Not always, but mostly, yes.
There's a beautiful fact about that.
What's that? Yeah, that's exactly the next thing I was going to say. Because of the time purposes, I will not do detailed math, but I'll skim through it. So suppose you have a symmetric matrix and you picked 2 eigenvalues and eigenvectors, okay? 2 of them. And then what do? I go take a x and inner product it with y. That's the same thing as x, A transpose y. And since A transpose and A are the same thing, these are all the same thing, right? Also, since AX is an eigenvector, this is lambda 1 times x by definition. And since this is an eigenvector, this is lambda 2 times y. Well, then when you write it out, it looks like this lambda is a number. You can take it out. Lambda 1 times x, y inner product. Lambda 2 times x, y inner product. And don't forget, this is x and y inner product. It's a number here. It's another number here.
and lambda1 and lambda2 are not the same number. So how could this happen? You take two different numbers, you multiply it with something, they end up being equal. The only way this could happen is this number is just 0, okay? So what does that mean? X inner product y is 0. That means two vectors are orthogonal to each other. So when you got a symmetric matrix, the eigenvectors look super nice. There's like one of them, and there's another one orthogonal, another one right there. So you can use the eigenvectors to even kind of decompose your space. It becomes a nice basis for you, right? Okay, and that's what we're about to do. And sorry for giving you all this stuff today, but I have to. Okay. Okay. So eigenvectors of symmetric matrices are orthogonal to each other. What is this good for? Collect all those eigenvectors. They'll give you a nice orthogonal basis for your space. That's what's going to happen. And bear with me for a sec before it happens, because you will hear this word called diagonalizable all over the place. What does that mean? There is like a diagonal matrix. Diagonal means only entries on diagonal. Everything else is 0. Okay. Wouldn't it be nice if your matrix would be just this diagonal guy? Of course, but usually life is not that nice, more complicated. So a diagonalizable matrix is, my matrix is A, but in essence, it's a diagonal guy. We just need to multiply it with some matrix P twice. P diagonal P inverse, okay? That's your A. Or in other words, let me write this equation this way. This is the same thing as saying diagonal stuff is P inverse AP. And why multiplying with P and P inverse from left and right doesn't bother me? Because multiplying with an invertible matrix is just a change of basis. Okay, that's what it means. A P matrix and P inverse left and right, I look at the same space from a different eye. That's it. Right? So that means, in essence, your matrix A is nothing but this nice diagonal matrix. All you need to do is kind of pre-processing your space. That's about it. So if your matrix will be diagonalizable, you'll be very happy. Why? Well, what does this diagonal matrix do? Takes the first coordinate of my vector, either stretches it, if lambda1 is like 5, stretching it 5 times. If this is like half, squeezing it, I could read off from the diagonal what this guy is going to do. Okay. So as soon as you realize your matrix is diagonalizable, you can read it off. So it becomes very easy to track down. But of course, somebody gives me a gigantic matrix. How do I know if it is diagonalizable or not, right? So this is for now just a notion. The good thing is, when you have a symmetric matrix, A, it is going to be diagonalizable. And the way it's going to come about, the diagonal stuff will be eigenvalues. I will go on this a little slower, don't worry. And the matrix, this P here, that was making clear your matrix is diagonalizable, that matrix is going to be given by the eigenvectors. So as soon as you have a symmetric matrix, the eigenvalues and the eigenvectors shows you that it is diagonalizable, and you can track down what this is going to do using those eigenvalues and eigenvectors. So how it is going to look like is this. I have a symmetric matrix, A transpose is A. I have real eigenvalues, and I have eigenvectors that are orthogonal to each other. Stack those eigenvectors next to each other. First column is first eigenvector, second column, second eigenvector. Last column, last eigenvector, okay? And if you take any of these two eigenvectors, say U1 and U2, they are orthogonal to each other, right? Inner product 0. In other words, if you take U transpose and multiply it with U, you will get the identity matrix, okay? And this is the type of matrix that precisely gives you the rigid motion. Okay? The type of the matrix that is U, where every column is orthogonal to each other, exactly what encodes rigid motion in whatever dimensions you're working on. It's just a small size remark. And then we also know, since there are eigenvalues and eigenvectors, by definition, when I multiply my matrix with the eigenvector, I get a number times the eigenvector, right? Now, when you see this,
if I take my matrix and multiply it with some vector x, a times x, and I want to understand what the heck is going to happen to my x, right? Well, if your x would be an eigenvector, then you would immediately know it's just going to get multiplied with a number. What if it isn't an eigenvector? What do? You use eigenvectors as a basis. You decompose your vector into those small pieces. And for every small piece, you know what's going to happen. For example, let's say the first eigenvalue was 5. That means if I give my matrix the first eigenvector, it's going to multiply everything by 5. It's going to stretch it. Say the second eigenvalue was half. That means if I give it the second eigenvector, it's going to divide everything by half, right? Now, think about those eigenvectors like small building blocks. Take your input x, decompose it into those building blocks. And every single building block, you know exactly what's going to happen. And you just, collect it back. That's it, okay? And the mathy way to write what I just said is this. Take your x, decompose it into eigenbases. Some number times the first eigenvector, some number times the second eigenvector, blah, 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 right? And now you might ask, how do I even find those numbers? Not so hard. This equation literally means x equals your matrix U times all these numbers a vector. In other words, U inverse x is all this stuff, okay? And then if you put all that together, you don't have to follow all this algebra. I'm just telling you once, so I do my duty. Please ask me more whenever you want, if you want to learn more. That means literally what you do. You take your vector x, you do this U inverse. It decomposes into this eigenvector pieces. You act on with the diagonal stuff, which is given by your eigenvalues. And you do inverse of this operation to recollect all that stuff and put x back to where it was. That's about it, okay? So as soon as you get a symmetric matrix, as soon as you know its eigenvalues, you know everything about it. People usually wouldn't want to bother computing all these eigenvalues. They would like to compute usually either the biggest or the smallest, okay? So now we are using all these data centers for machine learning. Say 20 years ago, we were using big computational power for physical simulations, mostly. Our military, say, needs to know weather predictions in a certain place. You need to do climate modeling or whatever else. It was mostly physical. And all the physical stuff is encoded by these eigenvalues. So your supercomputers were actually computing eigenvalues of a gigantic matrix all the time, okay, before deep learning took over. Right? So this basic thing models so much. And usually you don't even need to know all those eigenvalues, as I said. There are specific algorithms to compute the biggest one or the smallest one, or maybe top 5, depending on your application, okay? And this still is the thing for most people. Computing eigenvalues better, faster, more stable, etc. All right. Now, I just said along the way, if you have a matrix such that U transpose U is the identity, it doesn't squeeze or stretch your vector. It just rotates it around. In other words, it does not change the norm of your vector. It just moves it around, okay? This will be an exercise for you to think about if you want to. This is not hard to prove. You just need to think about it a little bit, and I'm happy to help always. All right, so this is symmetric matrices being diagonalizable through eigenvectors and eigenvalues. But not everything is symmetric. Then when I see a non-symmetric matrix, what do I do with it? I cannot use this technology. And the thing that gets around it is the notion of a singular value, okay? So we have eigenvalues and eigenvectors, goes back to this old Germans. Now we have an English word called singular value that works for even non-symmetric stuff. And there's a good chance you might be using singular values in whatever computation you're doing. They're all over the place, okay? If you heard of the word, say, PCA, principal component analysis, it's singular values. I don't know, if you're doing something on graphs and networks, likely you're using singular values. They're all over the place. What is a singular value? Well, suppose my A is not diagonalizable. I don't know what to do with it. Diagonalizable was nice. But one thing you realize is if you multiply A transpose with A, suppose you get a matrix X, take the transpose of this matrix, it will again be A transpose A. Turns out this X and X transpose is exactly the same thing. Okay, so A transpose A is symmetric no matter what A was, turns out. Then I could think about the same story for A transpose A and maybe relate it back to A. Maybe, I don't know. It looks convoluted, all right? But somehow it works out. And let me show you a picture of how it is gonna look like. Singular value decomposition of a matrix A will look like this. A will be equal to some matrix U, some diagonal, and some matrix V. And this U and V will be only moving stuff around. And the sigma in the middle will be diagonal. I'll give you more precisely in a minute. But let me tell you first the intuitive picture. It's okay. It's fine. Doesn't matter. It's just a technical detail. So what we are going to do in a couple of minutes, in the remaining 6-7 minutes I have today, is we will take any matrix and we want to do this diagonalize type trick on it so that I understand what this is going to do. Okay. Geometrically, suppose you take your V1 and V2 and the unit ball and say your matrix acts on it and spits out something like this. Stretches, squeezes, turns around. Okay. Right. Now, the singular value decomposition is going to figure out how this happened in 3 steps. First step will be moving things around from V1, V2. So you just move them around. Now, it looks like a nice basis for you. Then there will be a diagonal guy. It stretches the first one, sigma 1 much. And stretches or squeezes the second one, sigma 2 much. This will be the singular values, just like those eigenvalues, these 2 numbers. And then there will be another matrix moving things around again. Okay? It's going to be very similar to this eigen stuff, but instead of just one type of move, you will have 2 moves around. That's the difference. So in eigen stuff, what did we have? Let me show you once again. We had, where is it? Here. We had some move around, then the diagonal, then put back that same move, right? That's U and U inverse. In the singular, you will have 2 of them, U and V. That's the only difference, essentially. Okay? So the singular value decomposition looks like this. Every matrix A, even a non-square matrix that is not invertible, M by N, can be written as U sigma V transpose, where the first U is M by M. And this is the type of the guy that just moves things around, does nothing else. Second, sigma is a diagonal one. And the diagonal entries will be always 0 or positive. You will see nothing negative. It's super nice, okay? We'll only see either a positive number or 0. That's it. And this one, again, moving things around. So every matrix, you could take it and turn it into this singular value decomposition. First, move stuff around, multiply it with the diagonal, then move stuff around again, okay? So, for example, when we get the PCA, hopefully next lecture, we will take your data and make it like a matrix. Then we will look at the singular values. And suppose you want to reduce your dimension to 5. Then we will take the top 5. We will say these are the most influential directions. Then we will take the top 5 vectors from here. And from there, you will say, just look at those 5 dimensions. That's it. Okay. So singular values is a way to, again, read off what your matrix is doing. Even if it is not invertible, even if it is not symmetric, this still does work. Yes. No, there's no particular reason. They both have the same exact eigenvalues. Okay. And both definitions will give you the same output. PCA is a clever use of SVD. There are many other uses. This is the notion in the backend. That's one use of it that we will see in next lecture. But you might be using it for many other purposes. Okay. And now I have about 3 more minutes. Let me see what I want to tell you in the last 3 more minutes. Yes, so let me get into the zeros and positive stuff. When you do the singular value decomposition, you'll see some numbers out there. Some of them will be nice positive numbers, and there might be a whole bunch of zeros, maybe zeros, maybe not. Now let's think about what those zeros might mean a little bit, okay? So let's take, let me see, yeah, okay. All right, let me see what I want to do here. I think I can go to an empty page and write what I have in mind. Let's say my A was singular value decomposed like this. And let's keep it simple. Let's say my A had 3 singular values, sigma 1, sigma 2, 0. And suppose it's a 3 by 3 matrix, right? And let me take a 3-dimensional vector, x1, x2, x3. And let's see what A is going to do on this, okay? So AX will be U sigma V transpose X. And V transpose X, as I told you, is just the same X moved around, okay? Let's, to simplify it, say X perp. Same X, just I moved it around. Now, the sigma is going to go on this X perp. What is that sigma? Right here, sigma 1, sigma 2, 0. What this is going to do, it's going to kill the last coordinate entirely, right? For example, if your X perp happens to be 0, 0, 1, what's going to happen? You're going to get an entire like 0, 0, 0 out of this, right? Can you see? Because suppose your sigma is, say, 2, 3, 0. This is a diagonal matrix. I'm multiplying it with 0, 0, 1. The output will be just 0, 0, 0. That means your matrix A is killing some vectors. It's got some kernel. Some vectors are totally vanished by this matrix, okay? So as soon as you see some zeros out there in your singular value decomposition, that means your matrix has a kernel. Some vectors are totally ignored by this matrix. That's what it means. And sometimes it's useful. Sometimes you want to reduce the dimension by ignoring some parts. So it's not necessarily a bad thing, okay? So it's just what it is. You need to be aware, and we will use it for our purposes, okay? And I think that's the end of my time today. Thank you for the patience. It was a lot of notions today. But, you know, if I would teach linear algebra slowly, it will take a whole bunch of time. And that's not what we want to do in this class. So I had to kind of recap quickly. We'll keep doing a little more in next lecture, and I'll show you some applications, mainly PCA, and if we get time, linear regression. Let me stop the recording, but I could take as many questions as you want. I have time. If anybody needs to go, you can go.